Hey everyone, I'm gonna present our work on efficient fault tolerance for recommendation model training via erasure coding. So in this work, we present a new system called ECREC. This is a new approach to fault-tolerant deep learning-based recommendation model, or DLRM training. Some of the highlights of ECREC are that ECREC overcomes the downsides of checkpointing. It cuts the training time overhead up to 66%. ECREC allows training to continue during recovery, and it has really good scaling behavior with increased DLRM sizes. Before we dive into the designs of ECREC, let's cover some of the basics of recommendation system, what they are and how they're trained. So recommendation systems their purpose is to predict user preferences in order to serve advertisements and other personalized contents. These systems are widely seen on a variety of platforms, such as e-commerce, social media, streaming services, and so on. A typical recommendation pipeline looks something like this. We start off with a set of sparse categorical features. For example, user ID, item ID, view history. Some of these features, they can have a really, really high cardinality. For example, there could be millions, if not hundreds of millions of users. These features are then fed into a recommendation model that spits out some predicted targets. For example, click-through rate or stay time for videos, and purchase probability for merchandises. These targets are then combined in some way into a single score that's get fed into the ranker, and the ranker ranks the items based on these predicted scores. So then a deep learning based recommendation model, or DLRM, just means that we're using some sort of deep learning model as the recommendation model. A lot of cases, this is going to be neural networks. However, recall that neural networks themselves do not natively support categorical inputs, and therefore, we have to have this embedding layer in front of it. The key component of this embedding layer are just embedding tables. These are, essentially key value stores, with the keys being hashed features and the values being dense vectors. These vectors are learned representations of the sparse categorical features and are usually of length 32 to 256. Notice that there are two types of trainable parameters in this system. The obvious one is, the neural network parameters, what we call dense parameters here. The other type are the embedding table entries. These are the dense representations that we talked about just now, and we call them sparse parameters because they are embeddings to the sparse categorical features. To actually train such a model, people usually employ the parameter server paradigm, where we have a set of parameter servers that operate in a model parallel fashion, and we have a set of workers that operate in a data parallel fashion. So in a single training iteration, the worker ingests data from data shards. These could just be click logs. The workers then fetch the latest sparse and dense parameters from the parameter servers. They compute locally the gradients by doing a forward and backward pass on the computational graph. They push these gradients to the parameter servers. The parameter servers aggregate the gradients received from the workers and perform an update step. These training are usually done on a massive scale in the industry. There could be up to 1,000 CPU cores, and people nowadays also use GPUs on the workers to train. A single training of one model could take days, if not weeks. That being said, fault tolerance really becomes a problem in these training systems. According to an industry report, the mean time between failure is 14 to 30 hours on average. If you think about it, workers are naturally fault tolerant. If a worker fails, we could just restart the failed worker. However, parameter servers failing could really become a problem. This is because the embedding tables are all stored in volatile memory, such as RAM. And a system could use up to hundreds of parameter servers. And a failure of even one of these parameter servers could mean that we're losing part of the training state, and training cannot continue before we restore this portion of the lost training state. And therefore, a failure could halt the entire training. So, what are some of the ways that people have thought about to tackle this problem, right? The most common approach that people are taking right now is checkpointing. This just means that periodically, we pause the entire system and dump the training state, namely, values on the parameter servers to a persistent storage, for example, SSD or HDFS. However, this entails that we need a full pause during normal operation and recovery. This could mean a large time overhead. Again, according to some report, this could be on average 12% of the total training time, or 43% at worst. And this is over 1,000 machine year worth of computation per month at Meta, for example. The other potential way of doing, of handling fault tolerance is replication, which essentially just means that we're replicating the parameters in memory on one parameter server on another server. However, this just means that we need to at least double the memory usage, and it's pretty much impractical given that the embedding tables can be up to tens of terabytes. Therefore, introducing our work, erasure coded recommendation model, or ECREC. So the idea here is pretty simple. We are leveraging erasure coding to add redundancy on the sparse parameters. For those who are not familiar with the concept of erasure coding, this just means that we're encoding k embedding table entries from different shards to produce parity entries. If we take r equals 1, this just means that we have a single parity entry. The benefit here is that it reduces the amount of in-memory redundancy needed compared to replication. Let's illustrate this point with a simple example, all right? So if we take k equals to 3 and r equals to 1, namely we're encoding 3 embedding table entries into 1 parity bit. Suppose we have E1 being 2, E2 being 1, and E3 being 5. We write the parity entry as the sum of them, or 2 plus 1 plus 5, which is 8. Suppose server 2 fails. In that case, we would just recover the value on the failed server E2 by subtracting E1 and E3 from the parity entry, or 8 minus 2 minus 5, and we get back the entry on the failed server, which is 1. Note in this case that 20% of the data that sits in memory are redundant, namely P out of P, E1, E2, E3. That's 25%. Compared to, in replication, we want to replicate E1, E2, E3, and that's going to be 50% of redundant data. So, while all of that sounds promising, right, there are definitely some more questions for us to consider to design such a system that uses erasure coding. For example, how should parities be placed, and how should parities be kept up to date? So for parity placement, the first thing to note here is that we want to place the parity entries on a different server than any of its constituent entries. In this diagram, you can see that, for example, P0 is placed on a different server than E0, E1, E2, and the same for P1, P2, and P3. The other thing is we're using the rotating parity placement strategy, inspired by RAID 5 and storage systems. This ensures that the load of updating these entries are distributed evenly onto all of the servers, rather than all of the parities going to one server that stores parity entries exclusively. For parity updates, we designed this mechanism called difference propagation. This is pretty much needed for stateful optimizers. For example, in a dot grad, we have to maintain this cumulative sum of squared gradients across iterations for every parameter. To see why this is the case, let's walk through a simple example of how difference propagation works. So here, suppose we have this worker here. It computes the gradient for, let's say, this entry E2, denoted as gradient E2. It's going to send this gradient to the entry holding server S2. The optimizers on S2 are going to compute the updated value of E2 and the updated optimizer state for E2. And it's going to forward the difference between the original value and the updated value for both E2 and E2 opt, denoted as delta E2 and delta E2 opt, to the parity holding server S2. And S2 is going to update the values on, the parity values on its embedding tables. Well, the reason this is done compared to the worker sending gradient E2 to both the entry holding server S2 and the parity holding server S0, it's because on S0, we only have access to the parity instead of the original value of the optimizer state. And therefore, if we only have the gradient for E2, we cannot correctly perform an update step. This is why difference propagation is needed. So that is pretty much about the strategies for the sparse parameters. For dense parameters, before we go into that, there are some observations that we want to make first. The first thing is that there's this asymmetry between memory and network bandwidth footprints for DLRM parameters. On the memory side, the sparse parameters take up the most space in memory. To give you some sense of the scale, the sparse parameters could be terabytes, whereas dense parameters are usually just 100 megabytes. However, on the network bandwidth front, dense parameters take up the most because dense parameters are neural network weights. They got to pull by each worker on every single iteration, whereas sparse parameters, as their name suggests, are only accessed sparsely. The other thing we want to note is that erasure coding with difference propagation, which is the protocol that we described just now, requires 2x network bandwidth overhead for an update. With these points in mind, we decide that for EC-REC, we want to replicate the NN parameters by having workers sending gradients to both servers holding replica. This makes sure that we incur less network bandwidth overhead than erasure coding NN, and also it only incurs minimal memory overhead considering the very small size of dense parameters. And putting this all together, upon failure, we want to read the NN parameters from the replica, and we decode the lost sparse entries from the other original entries in the parity entry, as we did in the simple example just now. Further, to ensure free of pulse and consistency, we have granular locking that enables training to continue during full recovery, and two-phase commit to prevent losing in-flight updates while failure occurs. For the interest of time, we're not going to go into details of these. Feel free to refer to sections in the paper for details. Finally, evaluation. We evaluate our system on this curtailed terabyte dataset, which is pretty much the industry standard. It has 13 sparse features for a total of around sparse S equals 200 million entries in the embedding table, each embedded into a dense D equals 128 dimensional dense vectors. Model we use is DLRM for curtailed terabyte from mp4. This is a 7-layer MLP with these many features per layer. We varied the sparse parameter S dimension from 1 to 8x and dense parameter D from 1 to 2x. We benchmarked our system on a cluster of 5 parameter servers and 15 V100 GPU workers on AWS. Some of the evaluation highlights is that EC-REC reduces training time overhead on large DLRMs by up to 66% compared to checkpointing. On this diagram, you can see that on the very large model, there's a large decrease in the training time overhead. Further, what's more interesting is that EC-REC scales really well with increased DLRM sizes, whereas checkpointing almost is this linear scaling with increase in model sizes. And EC-REC enables training to proceed during recovery with only 7 to 13% drop in throughput, and it recovers from failure much faster than the average time for checkpoint. Finally, this is pretty much about it for EC-REC, a new approach to fault-tolerant DLRM training that overcomes the various downsides of checkpointing. If you have any further questions, please feel free to reach out to us. We have the contact information placed here on the screen. And thank you so much for watching this recording.